Assalamualaikum and hi everyone. In this video, we're going to learn about miscellaneous configurations. Before you proceed with this presentation, I hope you watched my previous presentation on emitter bias configuration. There is a lot of miscellaneous bias configuration. One of them is DC bias with voltage feedback, and another example is emitter follower and so on. So in this video, we're going to learn about the DC bias with voltage feedback. The difference between emitter bias configurations is the RB is connected to not directly to VCC, but it's connected to this point, which is we can say this point is VC, not VCC. So the equivalent circuits will be, keep in your mind, the good loop should be closed, which is it start from power supply and then it's finish at the ground. So in this case, for the BE loop, we're going to start with the VCC and then go to the RC, we go to the RB and then to the base terminal and then to E terminal and then RE. Finally, we have the ground. So this is complete loop for the BE loop. So for the CE loops, it will start with from the same point, which is VCC, and then it goes straight to the RC, and then for it should be go to the C terminal. After the C terminal, E terminal, and then go straight to the RE and then ground. So this, the blue one is the CE loop. So you can draw, start from the BE loop, which is we start from the VCC. From the positive terminal of VCC is connect to the RC first. We have the RB here, and then from the RB is connect to the base terminal. From the base terminal is connect to RE, and then finally it's connect to the ground. Okay, this is your BE loop. Okay, let me label first this one as a VCC and this one RC, and this one is RB. Okay, for the CE loop, maybe we can start from the VCC. So from the VCC here, this will connect to the RC. Okay, from the RC is connect to the C terminal, and then from the C terminal goes to the E terminal, and then we have the RE. After RE is connect to the ground. Okay, we just connect this one as to the ground. So this is the RE, this is the RC, and this is the VCC. Okay, this is your complete equivalent circuit. But keep in your mind that you have to label the current. Okay, which is here the current flow at the RC is not IB, it's IC. Okay, and then the current flow at the RB is IB, and then the current flow at the RE is IE. Okay, these are the simplifications. Same thing, which is we have the VCC and then RC, and then goes to RB, and then goes to the RE. Okay, and then we have the CE loop. Okay, CE loop I can say is almost same with the emitter bias configuration. Okay, and then KVL on BE loop, our target is to find the value of IB, IC, and also IE. KVL on BE loop, so let's start with the VCC. For the clockwise, it should be minus VCC, and then we have plus here, voltage drop at the RC. The current here is IC prime, and then we have the voltage drop at the RB. The current is IB, so this one RC. Okay, so IB, RB, and then we have the voltage drop at the VBE. This is where VBE, the value is 0.7, and then we have the voltage drop at the RE. The current is IE. Okay, so plus IE times RE equal to 0. In this configuration, to make our analysis easier, we're going to do some assumption, which is IC prime is almost equal to IC and almost equal to IE. Okay, if you still remember, in approximate analysis for voltage divider bias configuration, we assume that IC almost equal to IE because the IB is too small or IB almost equal to 0. Just substitute the value here, and then this equation will be minus VCC plus IC RC, and then maybe we can just put here RE. Okay, and then plus IB RB plus PBE equal to 0. And then what you need to do is you have to find the value of IB first in BE loop. So to find the value of IB, you have to substitute this IC with beta times IB. So we have the equation of IC beta plus beta IB times with RC plus RE, and then plus IB RB plus BBE equal to 0. So just rearrange this all equations to find the value of IB, and then you will have the value of the equation of VCC minus BBE over RB plus beta RC plus RE. So this is your IB, and then to find the value of IC, you just use the equation of beta IB, this, and then to find the IE if necessary, you can use this equation beta plus 1 IB, or you can just use the assumption just now, which is IC almost equal to IE. For the CE loop, I think is similar with the emitter bias configuration, so it's very direct. So we use KVL on clockwise loop, which is we have the positive VCC minus IERE, and then we have voltage drop at the transistor. Okay, and then we have the voltage drop at the C. So please remember that IC prime is equal to IC. So here I just use the value of IC, and then this one equal to 0. So actually this equation is same with the emitter bias configuration. So usually in CE loop we're going to find the value of VCE. So VCE is equal to minus VCC minus ICRC, and then minus IE RE. The load line analysis is totally same with the emitter bias configurations. Okay, so please refer to previous presentation. So what next? It is really recommended to do example question in textbook. For engineering students, I would like to suggest electronic devices and circuit theory. And then for the engineering technology student, I suggest the book of electronic devices. And then what next? To watch my next presentation on design operations. Oh, thank you for listening.